Right, so this is our walkthrough video for our Algebra 2 spring semester final. So I'll go ahead and work through these. Again, if you want, you can watch the entire video, or you can just kind of skip through to the ones you want to see, whatever's going to work best for you. So problem 1 here, we're looking at a system. So we're trying to solve a system. It's already solved for y for us, so it's going to be really easy for us to do substitution. I'm going to plug in this x plus 6 in for the y on the A original. You can do it other ways, but that's definitely going to be the easiest, probably the most efficient way to do this. So I'll have x plus 6 equals x squared minus x plus 3. So I have a quadratic. I have x squareds and x's, so I want to get everything onto one side and equal to 0 so that I can solve it. So move both of those over, and I'll have 0 equals x squared, now minus 2x, and then minus 3. So at this point, I can solve it by quadratic formula, by completing the like square, or by factoring, and factoring is typically going to be the easiest method here. So let's go ahead and try that out if we can. So if I use a little shortcut here, I'm trying to figure out what numbers are going to multiply to be negative 3, add to be negative 2. Well, it's going to be a negative 3 and a positive 1. So then my values for x are going to be 3 and negative 1. So not too bad to find those there. But just don't stop there, because again, that's only half of our solution. We still need the y values which correspond with each. So I can find the y values which go with them by plugging those values of x in to either equation and solving for y. The bottom one is definitely going to be a lot easier, because it's just x minus x plus 6 versus doing the value squared minus x plus 3. So I'm definitely going to go for the bottom one. So if I plug in 3 plus 6 is 9, so the first point is going to be the point 3, 9. My second point, plugging in a negative 1 plus 6 is going to be 5, so then my other point is negative 1, 5. So there's my 2 points, and typically we want to write those as ordered pairs. Again, if we have more than one solution point, you want to have the ordered pairs. If you're only getting a singular point, then x is this and y is that's fine, but the general rule, try and get in that habit. I have the there. You need the actual little box there, sorry. All right. So over here on problem 2, we're going to be trying to factor this one. So this is factoring when we have a value out in front here. So this is where we definitely want to do that little x in the box method. You can still do the x in the box method here for the factoring, but if there's not a value in front, this shortcut way is typically just a little bit faster and easier for most people. So 3 times 4 gives me 12 on top, and then I have negative 8. So I'm now looking for two values that are going to multiply to be 12 and add to be negative 8. So that's going to be a negative 2 and a negative 6. So then when I go to my box, I put the 3x squared in the top left, the 4 in the bottom right, and then I'll have my negative 2x here, my negative 6x here. Again, some people order this in a slightly different way. It's just how I do it, but it effectively does the exact same thing. Putting out my common factors, I can only pull out an x vertically. Here I can pull out a 2. It's going to be negative because this is negative. Going horizontally, I can pull out a 3x. So I pulled out the 3x there, and then down here I can pull out a 2 from both of these, and then it's going to be negative because, again, that's negative there. So I factors into 3x minus 2, and then x minus 2. And there it is, factored. Right. All right, so let's head down to 3 and 4. All right. So 3 we're going to try and multiply. And put this in standard form. So standard form is just like stuff like this, and we just had there. We're just doing the opposite of the factoring part now. You can do this a number of different ways. You can do it with distributive property. I typically, when I see 2 by 3s or larger, I just always do the box method because it's just a little bit more organized. It's not faster or slower, but it's really easy to tell what's going where. So I'm going to have 3x and negative 4, and then I'm going to have x squared, 2x, and 7. So to multiply all these, 3x and x squared is going to be 3x cubed. X squared negative 4 is a negative 4x squared. 3x and 2x is 6x squared. 2x and negative 4x is negative 8x. 3x and 7 is 21x, and 7 and negative 4 is going to be negative 28. So my like terms, if I have this organized correctly, are going to be in diagonals. So I can just combine my like terms, add like, kind of write down my final answer here. So it's going to be 3x cubed. Negative 4 and 6 is going to be positive 2x squared. 8 and 21 is going to be positive 13x, and then minus 28 on the end. So there it is, multiplied out. So again, just using that multiplication with the area model or the box method, whatever you want to call it. All right. 4, we're completing the square here. So this got tilted. All right. So I can draw out the box for it. If you don't need to do this, it's totally fine. It's actually a lot faster if you just kind of follow the kind of pattern. But I'll do this just to kind of help us all see it. So here's my x squared. I'm going to have 3 that I have to break up evenly onto both sides. So I can give 1 to each side, and then I need a half in addition to that. So this is 1 and a half, 1 and a half. So then what I end up with down here is 1 full part there, and then 1 and a half is, this is now a half, this is now a half, and a half makes a quarter. If I zoom this up a little bit for you, it'll look kind of like this. Here's my 1, my half, and my quarter. Right. So this in total, well, that's 1, 2 and a quarter, or 2.25, is how much I need in my little ones area. Right. So in order to get this to be a perfect square, what I need is x squared minus 3x plus 2.25. Now I can get that 2 different ways. I can either pull it from that existing 9, or the way that I do it, just so that I always do it the exact same way, is I add it and then I'm going to take it right back off with subtraction, 2.25, because now this is a net change of 0, so I haven't changed anything. I've just added the exact number that I needed. And then I still have that plus 9 on the end. So now this portion right there is my perfect square. This is equivalent to this box. So this box is just x plus 1.5 by x plus 1.5. So it's x plus 1.5 squared, hence it being the actual square and the term completing the square. So this is x plus 1.5, the whole thing squared. And then if I do the negative 2.25 plus 9, that's going to be a positive 6.75. So there is my graphing form for that equation. All right, heading down here to problem 5. So we're trying to round these to 4 decimal places. I have a variable in my exponent, so I'm definitely going to be using logarithms at some point here. But before I do that, I want to get this 2.15 to the x by itself, so I'm going to divide both sides by 3. And I'll get 2.15 to the x is equal 12 divided by 3 is oftentimes 4. So then we get that. Right, so once we're here, now we got to do that take a log of both sides trick. So I can take log of 2.15 to the x equals log of 4, because I can do whatever I want algebraically so long as I do it to both sides of the equation. So now why I do this is that property about logs, where I take the power and throw it out front. So now I have x times the log of 2.15 equals the log of 4. Well, now x is by itself other than this, so let's just divide that off. And I get that x is equal to the log of 4 divided by the log of 2.15, which, if we go to our calculator for that one, log of 4 divided by log of 2.15, and we get 1.8110. And there's the 4 decimal places which we needed for it. And there we go. All right. We're here in problem 6, another log problem, but here we already have a log. This is log base 5 of x plus 2 is equal to negative 2. So the only way that we know how to deal with this is to convert it out of logarithmic into exponential form. So this really says 5 raised to the negative 2 equals the interior, which is x plus 1. So 5 raised to the negative 2 power equals x plus 2. Well, 5 to the negative 2 is the negative will flip the fraction for it, so it's really 1 over 5 to the second, which 5 squared is 25. So I have 1/25, and I have to subtract that 2 over. So if I just do 1 divided by 25 and then subtract 2 from it, I get negative 1.96. There's my value for x. So I didn't need to round all the way to like 4 because this one ended or terminated a little bit earlier there. All right, on to the second page. So on problem 7, we're going to need to multiply these two things together, but we probably want to have everything factored first, so then we can cancel out a whole bunch of stuff. If you're given a problem like this, we're going to give you stuff that you can cancel quite a bit of stuff with. So always have it factored first because you can't cancel unless you're factored. So the top here, I want to factor that. That would factor into two things that multiply to be 10 and add to be negative 7. So it's going to be like negative 5 and negative 2. So there's the top factored. The bottom, that's the difference of two perfect squares. So that would factor into x minus 5 and x plus 5. And then over here on the right-hand side, top is just x plus 5. I can't make that look any better. I'll put it in parentheses so you kind of know, hey, it's already factored, but you don't have to do that. Then on the bottom, I can factor that one as well. So it'll factor into two things that are going to multiply to be negative 6 and add to be a positive 1. So that would be a positive 3 and a negative 2. So x plus 3, x minus 2. So at this point, a bunch of stuff should cancel. If nothing cancels, there's probably a problem with your factoring because I'm only going to give you these ones if they can factor at least, or can cancel at least somewhat. Right. So my x minus 2s, those can reduce out. X minus 5s, and then x plus 5s. So a whole lot of stuff's going to go away. So on top, there's nothing left, but there's always a 1. Because technically, again, these are giant 1s we are making. We're not just throwing stuff away. So I end up with 1 over x plus 3 is all that I have left. So a lot prettier than our original. All right. 8, if I want to subtract or add any kind of fractions, I have to get common denominators first. So in order to do that, I'm going to multiply the left-hand side by x plus 2 over x plus 2, and the right-hand side by x minus 1 over x minus 1. So then my top will be 2x plus 4 over x plus 2, x minus 1, minus 4x minus 4 over x plus 2, x minus 1. Now I'm leaving the bottom one factored because there's not really a benefit in me multiplying it out. I would if it would help me, but it's not going to help at all, so why do the work if it's not going to help us make it more simple or cancel things out? So on top here, I now have this common denominator, so I can write it as one fraction, all over x plus 2 times x minus 1. Again, just going to leave it factored because why not? On top, I can now combine some like terms. Now do not forget that this negative is going to apply to both of those two things there. So I could just make it plus and then minus on, and then change signs on both these right now, and then just worry about just adding them. It's a little bit easier. Or I can just think about it, this minus this, and so forth. Anywho, 2x and negative 4x is going to be a negative 2x over here, and then 4 plus 4 is going to be plus 8. I could pull out a common factor of 2 on the top, but again, that's not going to help me cancel anything out, so there's not a benefit in me doing it. It's not wrong, it's just not necessary. So we'll call it good, and that's our solution. All right, number 9 and 10. So these ones we're trying to do some composite functions here. So I'm going to be taking f, plugging it into g. So that's going to be 4 plus rad x minus 4, that whole thing squared. So there's my f of x being plugged into my g of x. So if I try and simplify this, I want to combine these like terms of 4 and negative 4. Those are going to just cancel out effectively. So I have rad x squared, which the square is going to cancel out with that radical, so I just get an x. On 10, same idea, plug the g into the f. Well, that would be 4 plus the square root of x minus 4 squared. Well, the square root and the square are once again going to cancel out for us. And I just have 4 plus plus x minus 4. And then the 4 and the negative 4 are going to cancel out again, and I get just an x. Now, these ones both give us x because they are inverses. I will tell you right now on your test for the final, they will not be inverses, but the process still stays the same. All that's going to be different is it's not going to turn out nice pretty. X is guaranteed. You'll just reduce it as much as you possibly can. All right. Down here to 11 and 12. So we're in the third quadrant, and we know that tangent is 5/12 in that area. So I'm going to go ahead and draw out that picture. So third quadrant, I'm down here. So it looks something kind of like this. So if I draw my triangle like that, there's my right angle. Here's my theta that I will go ahead and label. So my tangent is 5/12. So that's opposite over adjacent. So my opposite of that angle is 5. Adjacent to it is 12. So in order to find cosine or sine's ratio, I need that hypotenuse. So I can do a real quick Pythagorean theorem. A squared plus b squared equals c squared. So 5 squared plus 12 squared, and then square root that. We get plus or minus 13. It's only the positive option because we're talking about side lengths. So I get 13. It's almost like I picked a Pythagorean triple in order to make it nice, pretty numbers for you. So once we're there, my cosine of the angle is the ratio of adjacent over hypotenuse. So cosine is going to be 12 over 13. And our sine is opposite over hypotenuse. So 5 over 13. Now here's where the quadrant matters, because we really haven't talked about it much more than I drew the picture down here. In this quadrant, if you think about this as being my origin, I went left 12 and I went down 5. So both of those are actually negative values. The tangent's positive because I have a negative 5 over a negative 12, which becomes positive. But here, my 13 is always going to be positive. My hypotenuses are always positive for these. So my 12 is actually a negative 12. And my 5 is actually a negative 5. So we do need that positive or negative sign. A lot of you guys missed that specific part on your test. So don't lose easy points because of those positive and negative signs. That's why the quadrant there matters for us. All right, down to 13. So a few ways that we can approach this. But we know our base form is going to be y equals a b to the x plus c or k. I'll just use k because it's the value we've been using. Right? So k I know has to be 5 because the entire graph is shifted up 5. That's where my horizontal asymptote is at. So I'm going to have y equals a b to the x plus 5. So now to find a and b, I really need a system because I have two variables that I'm solving. I can get my first equation from plugging in 1/26, and then I can get my second one by plugging in 3/194. So let's go ahead and do that. So 26 equals a b to the 1 plus 5. And then 194 equals a b to the 3rd plus 5. So if I want to solve the system, I probably want to get one of those variables by itself. So let's solve for a here. I'll subtract the 5 and get 21 equals a b. Divide by b, and I get 21 over b equals a. So I can now plug that in to the a over here. I'll go ahead and subtract the 5 anyway and get 189 equals my a is being replaced by 21 over b times b cubed. Well, that b and that b cubed, I can cancel out that b with one of those b's. Now I have b squared. So I have 189 equals 21b squared. So to solve that out, I do 189 divided by that 21, I get 9. So 9 equals b squared. Square root, and I get b equals plus or minus 3. All right, so I technically have the positive 3 and the negative 3. We can't have negative values for that b, so I really only care about the positive 3. Again, I pointed out because you should always be in the habit of using the positive or the negative for when it does matter, but just know in this particular case, the negative is not a valid option for us. We only really care about the positive 3. So now that I know what that is, I can find A and say, well, A is 21 over 3, which is going to be 7. So I know what my B is, I know what my A is, I know what my K is, I have my equation now. So it's going to be Y is equal to 7 times 3 raised to the x plus 5. And there is my equation that models the situation. So again, I have specifically chosen relatively nice numbers for us, so we're not going to be getting crazy decimals. We're going to get numbers, maybe possibly some small but easy fraction. All right, so let's take a look at the last page here. So problem number 14, trying to determine all the roots for this particular equation. So I have graphed it for you so that you can see where your real root is. I do this purely so that you don't have to go and graph it and figure all that out. So, all right, this is crossing at 1. So the factor which gives me 1 is x minus 1. So don't forget to change the sign there and look at the factor, not the actual root. So I want to divide that from this. So I'll have x minus 1, and I'm doing my area model here, so I'm going to have x to the third plus 2x squared plus 0x minus 3. Again, you don't have to have that placeholder. I highly recommend it though, because it's a really easy place to make errors if you leave it off. So then my x to the third has to go here. So x times 1 is x to the third. Well, that's x squared. X squared times negative 1 is negative x squared. So now what plus negative x squared is 2x squared. Well, that's going to be 3x squared. What times x is 3x squared? Well, that's going to be 3x. 3x times negative 1 is negative 3x. And then what plus negative 3x is 0x? Well, that's going to be 3x. Again, that's why having that placeholder is important, because otherwise you'd say, oh, what makes it 3 or negative 3? And then, so what times x is 3x? That's going to be 3. 3 times negative 1 is negative 3. And I have no remainder, so I know that I did it right. Again, on these types of problems where I know one of the exact roots, it will always divide out evenly with no remainder. If I get a remainder, I know I did something wrong and I should go back and check it. Right? So factored, this is now x minus 1 and x squared plus 3x plus 3. So I factored it great, but I still want to find the solutions or the roots. I know one of them, this is going to give me 1. That's really, really easy. This one is going to give me my 2 complex numbers. So that's where I want to go to my quadratic formula for it. So if I go to quadratic formula, x equals negative b, so negative 3, plus or minus a big square root, b squared, which is going to be 9 minus 4 times a times c, all over 2a. So that's going to become negative 3 plus or minus big square root of 9 minus 12 is going to be negative 3 over 2. So that is going to be equal to negative 3 plus or minus I rad 3 over 2. So that, as well as 1, are my roots. So I have my 2 complex roots, my 1 real root, which makes sense because I should have 3 roots total from the x to the third power. So down to number 15. So we're trying to write an equation based off of this graph. So things that I want to look for are what's my amplitude, what's my period, what's my horizontal shift, what's my vertical shift. So vertical shift is probably the first one you want to find. So I'm maxing out here at 1 and down here at negative 3. So halfway in between those is this negative 1 line. So there's where my midline is. So I've gone down to negative 1. So that's one of the things that I need to know. Then I also need my amplitude, which is the height here, or the height here, which either way is going to be 2. So my A is 2. So now I need my period and my horizontal shift if I have one. So for period, I'm looking for what's the length of one full cycle here. Now I can kind of barely see it from right here to right here. right? But that might not be super easy for us to kind of tell. So you can just look for, well, here's a peak, here's a valley. So this here to here is half of one cycle. If I mirror that over, there's my full cycle, right? So the distance from pi over 4 to 5 pi over 4, the distance is pi. And then I'd have to go another pi over here to get that full cycle. And so that means my period is 2 pi. Right, so then the equation to find the b value, if I have the period, is period equals 2 pi over b. So I have 2 pi equals 2 pi over b. You can probably logic your way through what b is. B has to be 1. You can still solve it out if you need, but hopefully you see that. So b is 1, meaning that my period is not being changed here. Okay? But I do have a horizontal shift, because this would normally start right here, right? A sine curve would start on the midline and then start to go up. So that's what I should see. Sorry, that's what I should see for the start of it. Now I'm not seeing it here. If I go all the way here, I'm on the midline, but I start going down. So I could do the shift to the right, 3 pi over 4. Then I have to put a negative in front to cause it to go down first. That works and it is totally valid. But probably the easiest place to see it is all the way over here. That's the first place where I go up from my midline. And now that's a shift to a right, 7 pi over 4. So I would say y equals, my a is 2 times the sine of x. To go right 7 pi over 4, that's minus 7 pi over 4. And my whole graph got shifted down 1, so that's a minus 1 on the end. Now, with a periodic function, I can do a shift an infinite number of different ways. I could, if I knew, this would actually go left to pi over 4, or to negative pi over 4, and where it would start there. So I could also do this exact same thing, but say, hey, plus pi over 4 to shift it to the left that distance. I could also, and like I mentioned, I could shift it just to 3 pi over 4 and have it be minus 3 pi over 4, then throw a negative here. That works too. There's an infinite number of different ways that I could do this. Try and shoot for the easy ones, right? Don't just make it hard for the sake of making it hard and being different, right? Okay. So there is my solution to that one. And that is the end of our test, right? So hopefully that helps you, and good luck on your final.